Okay, off we go. Picking up where we were last time. So we were talking about integrals and spherical coordinates, and we were mostly done. There's a couple more examples I want to talk through, at least to some degree. So here we have a new domain to think about. This is what it looks like, of course, right? Three-dimensional ball centered kind of, off of the origin, onto the y-axis there. And the first thing you're going to notice about this is, oh, cool, this is a sphere that's with its center on an axis, and that's, goes through the origin. My gosh, we just did one of those. That's what the last example that we did. This one was centered on the z-axis. This one is centered on the y-axis, but whatever. I mean, all the variables are kind of interchangeable in some sense. And so you might think this is going to be practically identical. It's not. Right? This is a significantly different example. And the reason is that the z-axis that this one was centered on is special in spherical coordinates, right? That is the axis that phi is measured off of, specifically z, right? It is also the axis that theta is measured around, right? So as far as spherical coordinates are concerned, X, Y, and Z are not really all kind of interchangeable. They're significantly different. So we're going to expect to get a meaningfully different answer here, and we will. Okay, so our usual process. Well, first of all, procedural point. Rho squared sine phi d rho d phi d theta, right? Don't forget to get that stretching factor in there. Get those points in the bank, right? And of course, have your differentials in what I'm going to call the right order. Okay. All right. Now that said, starting with our theta slicing, here's what a theta slice looks like. Now this is a purely geometric appeal, but if you take a ball and if you slice through it at an angle as drawn, kind of like this, I claim you're going to get a sort of a disc cross section. Geometric appeal. That seem reasonable? Next geometric appeal that I'm going to make is that if you ask, well, what's the lowest value of theta where you actually get such a slice, or where do our such slices begin? I claim it's theta equals 0 where those slices begin. Now, it doesn't seem right. You might look at the picture and start thinking about the geometry and think, look, if I'm there and if I start going in the X direction, it's a swing and a miss. I don't actually hit anything in the ball, because the ball is exclusively, except for the origin, it's exclusively in the sort of positive Y portion of space. But the thing is, no matter how little you swing into the first octant there, and no matter how much you swing with, toward a positive value of theta, even the slightest little bit of positive theta, and you're gonna swipe off just a little bit of that ball. Does everybody see that? Now, it's another geometric appeal. Right? All right, and then analogously, as theta goes around, it's going to sort of stop where theta is equal to pi. That same geometric case, just kind of on the other side. Okay, how we doing with the theta bounds? Does everybody see that? Just gotta think about the geometry, kind of visualize it three-dimensional. Okay, now as y'all will recall, I like to redraw the theta slice. You don't have to, but it can be convenient. When you're trying to think about values of phi, if you're looking at this picture on the left, those phi angles will look distorted because of the perspective, right? You're looking at things at a weird angle. If you redraw it where you're looking straight at it, it's just a little bit easier to see. Highly optional. Anyway, that noted, let's think about our phi values. That's what you might call a phi slice. And let's think about where they start and end. And again, it's one of these things where, well, there's sort of really small values of phi, and then as you increase phi, those slices get bigger and bigger for a while, and then they start to get smaller and smaller again. And it's eventually they start to get vanishingly small. And again, the sort of starting value of phi comes from where you're going straight up, where you don't actually have a slice, right? You only get the origin. But anything larger than 0 will have you have a good sized slice. And then likewise, as phi goes around, right, or sort of last value of phi is going to be, wrong color, red, sort of straight down like that. And so 0 to pi again for the phi bounds. What do you think? Is everybody, yes?
So phi's kind of like that, and then theta's like this.
Yes, theta is the angle that's measured sort of this way, sort of around the z-axis, and then phi is the angle that's measured off of the z-axis. Yeah. Yeah, and it is super frustrating that of all the letters of the Greek alphabet that they had to choose from, they chose the two that look most alike, arguably. So that's a little frustrating. And then, of course, we've talked previously about how physicists like to switch their roles. So it's all for maximum confusion, right? Very frustrating. Okay, anybody else? All right, let's see here. Now, proceeding along, we want to think about the next bounds. Now I want to think about rho. So we're going to imagine a particular phi slice of our, let me just do it like this. Particular phi slice of our particular theta slice. And that's where we want to start thinking about the range of values of rho. And rho, of course, starts there. Now, don't forget, if you have redrawn your picture like I like to do, don't forget to reinterpret, but where did that actually come from in our original picture, which, of course, would be there, which is the origin, where, of course, rho is 0. And then let's see here, we're going to end our last value of rho, that point, which is going to be something about there. And what can I say about this red point on my original picture? Well, it's geometric appeal, but it's going to be somewhere on the sphere. And as with several previous examples we've seen, if you want to know, here we need to know the spherical equation for that sphere. What you do is you take your given particulars, you write the rectangular equation, then you do a chapter 1 style conversion to get you the spherical equation, and what you'll get is that right there. Now, I just yada 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 a lot of details, right? That's all chapter 1 stuff though. Make sure you can do that. Right? This is a good exercise to make sure you can derive that equation. Devil's in the details. So you want to discover now, not during the exam, if you perhaps might have a rough spot in your understanding that needs to be figured out. Okay. All right, and again, we're trying to find a rho bound, so we solve for rho. Thankfully, already done. And there you go. Is everybody happy? All right, let's see here. On to the next. This is the last example I'm going to do for spherical coordinates. I'm not even going to do most of this example, by the way. Really, the purpose of this example is to show you what I'm going to call kind of an art trick. I think this is valuable. Sometimes what you're drawing is really hard to draw. It's really hard to visualize. And if it's hard to visualize, then it's going to be hard to draw valid conclusions, right? So this is not for the purposes of making your drawings prettier. This is for the purpose of avoiding mistakes, right? Being able to have a picture that's good enough to help you avoid mistakes. All right, so what you'll notice here, we have a ball, and this other one. It's tempting to call that a ball also, but notice that's a greater than or equal. That means this says we're only interested in points that are in the green, but also that are outside of the red ball. So outside of that. And so all together, I mean, what's in the green but outside of the red, it's a little bit hard to draw. It's kind of this sort of a thing like that. And this is a poor drawing. It's a poor drawing because it makes it look like there's a vertex there, which of course there is not, right? We've got a round scoop of ice cream, let's say, and then the same ice cream scoop that made this round scoop of ice cream, we scoop a scoop out of the bottom of that scoop, right? And so it doesn't have a corner. It's got kind of an edge there around. But there's also, I mean, I could draw that edge, but if I draw it like this, then it makes it look like it's sort of solid. But again, there is this kind of cavity, this indentation in there where we scooped out that little bit of the ice cream, right? It's just hard to draw. When things are hard to draw, it makes it harder to visualize. And when they're hard to visualize, it's harder to slice them up and make, again, valid conclusions. So here's the artistic trick that I think is my main motivation for having this example in here is this statement right here. So a cross-section of an intersection is the intersection of the cross-sections. Let me explain what I mean by that. We are interested in what I'm going to call an intersection. This region, and I'm going to just go ahead and go with my bad drawing of it here. It's technically, literally, it's not the intersection of these two balls. The intersection would be this thing here. But this is the intersection of, you might say, the inside of this sphere with the outside of that sphere. So, suitably interpreted, this is an intersection. All right, and we're interested in taking cross sections of this because that's how theta slicing works. Cross section would be, I want to figure out how to take a slice like that. Now look, you may be really good at visualizing things three-dimensionally. If you are, that's fantastic. That's great. Some of us, not so much, right? And, I've been around the block enough times, I could do this one too. But I do still think it's easier with the following trick. Trying to understand how this theta slice looks of this blue intersection. What I'm going to do is I'm going to look at the individual cross sections, not the cross section of the whole of the the full intersection. I'm going to look one ball at a time. What do those individual cross sections look like? And that's actually easy to draw. If I take a ball. By the way, let's get rid of that. If I take this ball here and I ask, what's a theta slice of that ball look like? Well, nothing to it. It's a half a disc. Super easy. That's effortless. And then I say, okay, fine. What about the other cross section? The cross section of that ball. Oh, again, well, it's a ball. The cross sections are discs. Nothing to it. And as you see, as I have here in the statement, what I want to do is take the appropriate intersection of those individual cross sections. So since what I was interested in originally was the part that's inside the orange but outside the red, I'm going to do the same thing here. Inside the orange, outside the red, and that gives us this, well, again, kind of hard to draw thing here. I had it shaded in gray. Now I'm shading it in purple. And to my eyes, I visualize this as being kind of like an eagle talon. I don't know, I think it looks like kind of like an eagle talon. And look how easy it was to draw. I focus on the individual cross sections and then take the appropriate intersection of those. And I avoid having to think about the difficult to visualize, difficult to draw three-dimensional solid pretty much entirely. Does everybody see the move there? Everybody see how that makes our lives a little bit easier? Any questions? Okay. All right. So, and then, details to follow. The details are analogous to stuff we've already done, so I don't want to spend a lot of time on this, but you can think about the range of that. Well, the theta goes all the way around, of course, and then phi slices come out of angles like that. Well, your first one is there. Your last one is there. You notice the first one is obviously phi equals 0. The last one, we have a lucky break, little equilateral triangle. You gotta love it when that happens. And yada, yada, yada. So make sure to fill in those details. Okay, so that finishes 5.5 part 2. On to 5.5 part 3. This is not really one of the main focuses in the book, but I think this is a really important topic, and I'll try to justify that in a bit. I think it's an underappreciated integration technique. This is one of my all-time favorite integration techniques. Right? Okay, so I want to remind you, first of all, of something you already know. If you go back to single variable calculus, we have this theorem. It's not written in that form in a single variable calculus class. In a single variable calculus class, they'll say integral from like negative a to a of f of x dx equals 0. And the difference in how I've written it is I've written the integral from negative a to a as an interval that is symmetric, what I'm going to call symmetric. So by symmetric, what I mean is that it is its own reflection over the origin. And I'll just draw a quick picture here. If there's your x-axis and there's the origin, and if this is where negative a is, and if this is where positive a is, this symmetric interval, like so, when you reflect over the origin, nothing happens. It is its own reflection. And symmetric is a natural word choice for such a set. So, again, you probably see it written like this, rewriting it like so. Now, to be clear, what the statement of the theorem is, if your domain is symmetric, as we just described, and furthermore, if your integrand is odd, and flash back to Calc 1 or 2, somewhere along in there. This is what odd means. It means that when you reflect the input, you negate the output. Does everybody remember this? F of negative x being negative f of x. Odd powers of x have this property. And so we call such a function an odd function. So anyway, it's a pretty cool theorem. In a case where you have a symmetric domain and an odd integrand, boop, 0, done, no anti-differentiation. You don't have to use the fundamental theorem of calculus. It's just pow, 0. Does that look familiar, I hope? Now, I'm going to try to justify why this is true. You could probably see this coming as to why I'm doing this. Anytime I'm talking about single variable calculus is because this is going to lay the groundwork for an extension to a multivariable equivalent. So everything we're doing here, we're about to see multivariable equivalents of those ideas. So in particular, this Riemann sum argument. If you've got your symmetric domain here from negative a to a, then whatever term in the Riemann sum you might be looking at negative p, and the corresponding term in the Riemann sum that you might be looking at for positive p, notice those two terms in the Riemann sum, because of the oddness, because of this corresponding minus sign, those terms in the Riemann sum cancel. All the terms in the Riemann sum pair up and cancel each other, and thus you're left with 0. So I think this is actually a pretty intuitively satisfying way to see, why this theorem is true, why it sort of should be true. Here's a different take. And this is the one that I think is really kind of better. And it's not. We don't have to decide, but this is certainly better in one way. We're going to use a change of variables. And remember, our single variable change of variables is just substitutions. What a lot of students call U substitutions. Whatever. Okay, all I'm going to do is I'm going to use x equals minus u. So said differently, my change of variables function, g of u is negative u, right? A reflection, reflecting over the origin. I'm going to use that as my change of variables, and check it out, everything just kind of falls apart because, well, by assumption, our domain is its own reflection because it's given to be a symmetric domain. That means I am effectively looking at an integral over an image. And when you have an integral over an image, you can do the change. Oh, I missed this. You can do a change of variables pullback. Right? You pull back to the original pullback domain. Don't forget to plug in for what x is. X is g of u, which of course is minus u. And don't forget your stretching factor. So it's just change of variables. Or again, in single variable language, that's just a substitution. And then you notice, okay, well, let's see, by the oddness of the integrand, f of minus u is minus f of u. And we're done, believe it or not, because check it out. This integral we now see is its own negative. What could the value of this integral be that is its own negative? And of course, 0 is the only number that is its own negative. So, boom, lovely little argument, and change of variables is what gets us there. What do you think? Everybody follow the idea? Okay. All right. We're going to do multivariable version of all of these ideas now. And when you're in 2 dimensions instead of 1, a reflection, you don't reflect over just a point like the origin, you reflect over a line. But it's still fundamentally the same idea of a reflection. Just go sort of through what you're reflecting through, sort of to the opposite side. It's where your mirror image would be, right? Okay. Likewise, odd means exactly the same thing. Odd means that when you reflect the input, you negate the output. Just shamelessly stealing the single variable idea of oddness. Now we have this new idea of oddness over a line for a function of 2 variables. And then likewise, we're going to totally rip off our old idea of what does it mean for a domain to be symmetric. It means it is its own reflection. It means when you reflect over the line, nothing happens. Looks exactly the same. And then guess what? The theorem totally still works. The exact same theorem. If you're doing an integral over a symmetric domain of an odd function, that integral is 0. No having to use the fundamental theorem of calculus, but wait a second, it would have been even worse than that. I would have had to do a slicing thing and worry about corners and worry about side swipes and oh my gosh, how many iterated integrals am I going to need and all of that stuff, and you don't have to do any of that. No slicing, no dicing, no anti-differentiation, no worrying about how the ugly formulas for the inner bounds will get into your outer integrand and none of that. 0. Walk away. Everybody see how crazy convenient that is? All right, now we're going to show you a few examples of how to do this, but I do want to emphasize a couple of landmines you got to be careful about. You do have to make sure that both conditions hold. Again, I like to make a big deal out of things where I see students make mistakes on previous year's exams, and one of the common mistakes that I see is students will look at some double integral that comes up naturally in some context, and they see a domain that's symmetric, right? And oh my gosh, symmetric domain, and they say integral is zero by symmetry. They didn't even check to see if the integrand is odd. You gotta have both conditions. A symmetric domain by itself means nothing, right? And then the vice versa. Just make sure you have to check both. The other thing is you have to use the same line for both, right? You can't have, this does not work if your integrand is odd over one line, but your domain is symmetric over a different line. It just doesn't work. So let's try to see why that is, and why does this theorem work? And you can even kind of guess the arguments I'm going to make. What I have here is just a kind of a copy paste of the single variable argument we made previously. It's now double integrals instead of single integrals, and it's dx dy instead of just dx. But same basic idea. If it's symmetric, then the domain is its own reflection. We pull back through the reflection back to the original domain, which of course is the same. You plug in the change of variables function as usual. Don't forget your stretching factor, and if you think about it, if you reflect, it doesn't even matter what line you reflect over, any sort of reflection preserves areas. Reflecting never made, this is not a funhouse mirror type situation. It's regular old, nice, flat reflections preserve areas. So stretching factor is 1. And then oddness, when you reflect the input, you negate the output. Again, just exactly like we saw in the single variable case. We again now have that an integral is, let's just try that again. An integral is its own negative, and therefore that integral has to be 0. It's the same argument, just now two-dimensional instead of one-dimensional. So, if you get a little confused with this argument, if there's some part of this argument where you're like, oh, wait a second, what's going on there? Look back to this argument. This is single variable calculus with unusual notation. But this is ultimately literally single variable calculus. Think about whatever it might have confused you about the two-dimensional theorem. Think about the analogous step here, and then that is your guide on how to interpret over here. Okay, now let's see the Riemann sum argument. And again, it pairs up pretty nicely. If your domain is symmetric over a line, then one term in the Riemann sum and another term in the Riemann sum, those two terms in the Riemann sum, they'll always pair up. Right? You got a symmetric domain, so any little piece of area here is a corresponding little piece of area there. By the oddness, we know that f of a reflection is the negative of the original f. That's oddness, which means these two terms cancel. Just like in single variable. Everybody buy this idea? All right, let's see an example. Excuse me. So, here we go. We've got, oh my God, this is a nasty integral. Yikes. Really don't want to have to compute this the old-fashioned way. First of all, look at that integrand. It's already, I'm not happy, right? Second of all, if you draw what your domain looks like, by the way, this is a Calc 1 prereq thing. So make sure that you can draw at least qualitatively. Come on, I can do better than that. So yeah, this curve is approximately like that, and this curve is about like that, and so our region here, the region bounded in between, is this shape. And think about it, if you were to slice this up, let's not use symmetry real quick. If you were to slice this up, of course you're going to do the slices like this. The upper bound for your y's then is going to be x squared minus x to the fourth. So when you do this inside integral, you're going to be plugging in for y, x squared minus x to the fourth. Now you got x to the fourth times sine x, which means you're going to have to integrate by parts 4 times. Right? Anybody want to do that? Right? That sounds super tedious and irritating to me. Right? I would love to not have to do that. Plus, I'm still scared of this. Right? So this is ugly business. All right. So here's the much easier way to do it. This is symmetric domain. Right? You just take a look at it. Is everybody willing to buy that this is symmetric? In particular, this is symmetric over the y-axis. Now that's just a geometric appeal. If you'd like to see an algebraic take on this, notice that a reflection over the y-axis has this formula, right? A point here, when you reflect over the y-axis, turns into a point that has the same y-coordinate. But when you do this reflection over the y-axis, the x-coordinate is going to get negated. Right? So there's your reflection formula. And if you plug that reflection formula in to see what this green equation turns into, it turns into exactly the same equation. So that curve is its own reflection. And I think it's honestly an easy pitch that the blue curve is clearly its own reflection, and therefore this orange region is its own reflection. Y'all buy that? Does it seem reasonable? We got ourselves a symmetric domain. Now let's think a little bit more carefully now about the integrand. I mean, you do have to do both. You got to think about that integrand. So color choices. I used all my best colors. You know what? I don't think I need these colored anymore. I don't need any of those colors. Okay, there we go. Okay. So, keeping in mind that our reflection is just going to negate the x. Here's how you reflect over the y-axis. And our big question is this function odd? And at a quick and casual glance, it's really hard to tell, right? It doesn't leap off the page. It's really not clear. But what you can do is just think to yourself, well, look, when you reflect, the way we test oddness is we reflect the wrong colors. We reflect the input as per our reflection. Now, of course, that means that we're going to, everywhere we'd had an x, we're instead going to put minus x. Right? We reflect the input, and then we want to see, well, are we going to get the negative of the otherwise output? Does this negate the output? And you go through and you do the algebra, and you see, where does that minus sign go? Well, it gets cubed. So where does this minus sign go? Blah, blah. This minus sign. Oh, wait, how does sine work? This trig function, sine. You got to remember your trig symmetries. Right? Does everybody remember all of that from way back when? Right? And sadly, I'm sorry, but those facts just never really quite go away. So make sure you're good with those. And happily, the answer is yes. When you reflect the input, you negate the output. Everybody all right? So we win. This integral is 0. Whoops, I didn't mean to delete the whole. Try that again. We have a symmetric domain, an odd integrand. That integral equals 0 by symmetry. And I didn't have to do any antiderivatives at all. Right? If I had to actually brute force, 5.2 style, actually crank out this double integral, that would be, I don't even know if I could do it. And instead of having to face the possibility we can't even do it, I had to draw a picture and I had to think about how reflections work and I had to do a calculation for odd. Not that bad. A little bit of algebra and boom, we're done. We win. Ever see the power of this tool? Very powerful tool. All right. Now, here's the good news. You don't have to write all of this down every time. Most people don't. Right? You just have 4 requirements if you want to make a symmetry argument in this class. And I think this is a pretty light load. You do have to actually tell me what you're doing. You do have to say the word symmetry somewhere to give me the indication that, okay, you're making a symmetry argument. Okay. You do have to actually run it into the end zone. You do have to point out that, so that means your integral is 0. You got to write that down as well. You got to tell me what the line of symmetry is. And in particular, what I mean by that is you have to tell me by what line of symmetry are you claiming that there is a valid symmetry argument. In other words, you have to tell me what line of symmetry are you, is the integrand odd and the domain is symmetric, and therefore that you draw this conclusion. Sorry, I got a hiccup here. And then, of course, I hope this goes without saying, but you do also have to be correct. If you can't, obvious, right? Of course, you have to be correct. But this is a dangerous point. It is sometimes the case that a student could tell me a line of symmetry and maybe the domain is symmetric over that indicated line of symmetry. But here's the problem. If you just say, oh yeah, here's a line of symmetry and my domain is symmetric, if the integrand is not odd, then that's not progress toward a solution. That's progress toward a dead end, which is not progress. Right? So there has to actually be a valid symmetry argument. In other words, you have to, you can shortcut you can abbreviate your answer, but there does have to be an actual answer there that you are abbreviating. So I hope that makes sense as well. And this is why it's dangerous, because if you're one of these students that, very understandably sees a beautifully symmetric domain and thinks, okay, well, come on, look how beautiful that symmetric domain is, and just figures there's got to be a symmetry argument. If there isn't, then it's you didn't actually do anything that actually helps to solve the problem. So you got to watch out for that. It is possible to think that you're done and actually you haven't even started yet. And you can imagine from a strategic point of view on an exam, if there's no actual progress toward a solution, what do we do in terms of partial credit? As much as we want to, there's nothing there, right? So don't accidentally skip a question, in other words, by being a little too careless as you think through the argument. So my advice is think this through pretty carefully, even if you don't have to write it down, right? But still, think it through. Make sure that the symmetry argument actually is there. And only once you're sure that there is, in fact, a valid symmetry argument, then you can say, oh yeah, this is equal to 0 by symmetry through whatever your line of symmetry is. Okay, how we doing? Everybody see what the policy is on that? All Okie dokie. So yeah, be careful. Heads up. Right? Don't want to get burned. Okay, here's another example. The main purpose of this example is to talk about how to find the formula for the reflection. There's a lot of little micro details in here. Y'all can see those for yourselves. For example, this domain I claim looks like that. Think it through. Make sure you're good with concluding this. Now I claim, something to think about, but there's a line, missed. There's a line of symmetry like that. Make sure you're confidently comfortable that that's a line of symmetry. And now let's ask, how would I find the reflection formula? By the way, why do I need the reflection formula? It's not on this list of requirements. You're not required to give me the reflection formula. But you are only going to get credit if there actually is a valid symmetry argument. You can only know that there's a valid symmetry argument if you know that this integrand is actually odd. How would you know this integrand is actually odd? The fact that the numbers here are odd is not enough to do it. It doesn't work. You have to look at the whole thing, and how the reflection works, it's really not obvious how this is going to work. So I think you need to know the formula for the reflection, and notice if you have a point there and you reflect, get a point there, it is not immediately clear what the relationship is between the coordinates of these points. This point here is not the negative of this point. Right? The negative would be way over there. So how do we find the formula for the reflection? That's going to be our main focus here. The formula for the reflection, well, here's our line again. And I like to think in the following terms. Whatever input point you have, it has an x coordinate and it has a y coordinate. I'm going to suggest that we not think about this point in terms of an arrow coming out of the origin. Think about this point in terms of what I'm going to call its little rectangular frame there. And if you think about the rectangular frame, what's very convenient is rectangular frames, when you reflect over a 45-degree line, rectangular remains rectangular. That horizontal blue line segment becomes a vertical line segment. And that vertical green line segment is going to become a horizontal line segment. And therefore, putting in the point x comma y, this reflected output point, negative y comma negative x, and it's just a matter of looking at that rectangular frame and thinking, okay, well, what's the x coordinate, what's the y coordinate? Oh, and that was positive, so this thing's negative, and you just look at that picture and think about the geometry, and that'll give you this reflection. How we doing? Everybody see how to do that? And then once you have this reflection, then you can persuade yourself. It's just kind of a matter of plugging in. You take this reflection, you plug it into there. This becomes that, and you chase it on down, and sure enough, you get the minus sign that you need. So it works. Integral 0 by symmetry. Okay, so even though the rules don't tell you that you have to write down the formula for the reflection, you have to write down the demonstration of it being odd, kind of de facto, you might actually kind of have to anyway. Because otherwise, you're taking kind of a wild guess, an enormous risk that maybe that isn't odd. And so you really need to get that confirmation. Okay, here's another example. This is one of the landmines. I have seen students crash and burn on things like this. And by the way, I don't set these landmines on purpose, but they come up naturally in the real world, aka your engineering classes. Right? You will encounter situations where you have a symmetric domain, but the integrand's not odd. Or you have an odd integrand, but the domain is not symmetric. Or in this case, both but by different lines. And the devil is in the details. So let's draw it. Our domain has these corners. Here, our domain is this triangle. Oh, nice and symmetric. You gotta love it. Here's what a lot of students will do, and I've seen this ever since I was a student. I saw friends of mine do this. I don't think I ever did this myself, but oh God, maybe I did. Anyway, oh my gosh, it's symmetric. Oh my gosh, look at my integrand. My integrand is obviously odd. Check it out. It's a power. It's an odd power. It's the textbook definition of odd. Symmetric domain, odd integrand. Boom, 0 by symmetry. Students will write that down, turn the page, never look back, and not realize until they get the test back that no, that doesn't work, that there is no such argument, and they get 0 on that question. Right? Which is, oh my God, what a catastrophe. The detail, of course, being that the domain is only symmetric over the y-axis. Reflection over the y-axis negates the x-coordinate. And negating the x-coordinate does not make this function go negative. It just doesn't. We would need to negate the y. Right? This function, said differently, is only odd over the x-axis. Because reflecting over the x-axis is what negates the y. Does everybody see the problem there? Why this does not work. There is no symmetry argument. It's not that the student didn't show the whole symmetry argument. It's that there is no symmetry argument, and any suggestion that there was is just wrong. So it's very dangerous. Be careful, right? Watch out for this kind of nonsense. And again, I'm not the bad guy here, right? I'm telling you, life will create these circumstances naturally. Okay. All right. Last thing to say: 3 dimensions. Oh my God, the exact same thing. 1 dimension higher, of course, but we don't reflect over points. We don't reflect over lines. We reflect over planes. Every time you look in the mirror, that's what we're talking about. Right. Whoops. Again, what do we mean by an odd function? A function is odd if reflecting the input negates the output. I stole that straight off of the 2-dimensional. It's just that now we're reflecting through a plane. What does it mean for a domain to be symmetric? Well, it needs to be that the set is its own reflection. Same exact thing. And again, we have a theorem. Again, the theorem has the same conditions. I just need to have a odd integrand over a symmetric domain. Both applying and both using the same plane. Your integral is equal to 0 by symmetry. Same exact result, same exact, 1 dimension different, right? But morally equivalent. Okay, so nice little example here. This would be a pretty terrible integral. Now, the domain is the unit ball. We saw back in 5.4 that if your domain is the unit ball, there's square roots everywhere. We improved things by realizing, hey, I could do this in spherical coordinates. But if you do this in spherical coordinates, there's going to be trig everywhere. Right now, all else being equal, much better. Constant bounds. Single iterated integral. Much better. I'll take trig over square roots any day of the week. Right? Lots of painful personal experience. I will take trig over square roots any day of the week for sure. But still, when it's a lot of trig, all else being equal, I'd kind of prefer not to. So here's the cool observation. Let's use the XY plane. Reflecting through the XY plane will negate your z. When you negate the z, that makes the integrand odd. You can carry that through, right? There's a bunch of details there, but it's just if you stick a minus sign on your z, that minus sign gets cubed. That results in the minus sign that gives you the oddness. Of course, the domain is symmetric, integral 0 by symmetry, and we're done. And we don't have to deal with that. Let me give you one last thought, super quick. You might find this amusing. So again, second major in physics, I did more integrals than you're ever going to be able to shake a stick at, right? My honest, in fact, conservative estimate, 20%, this is a conservative estimate, 20% of the bazillion integrals that I did equals 0 by symmetry. I think that makes this possibly the most important integration technique to know, right? And y'all are mostly engineers. It's not quite the same as physics, but it's not that different. So keep on the lookout in your engineering classes. Quite possibly 20%, maybe more of your integrals will be 0 by symmetry. Y'all have a good weekend. See you later.